Here's a strange fact to start with. You can run out of inodes on a disk that's half empty. That single sentence tells you almost everything you need to know about what an inode really is and why it matters. In this episode of IT 3000, we're going to unpack the inode, the quiet little metadata record that is in truth your file's real identity. The name you type, that's just a label pointing at it. So let's pin down the concept. An inode is a fixed-size record on disk that holds everything the system needs to know about one file: its type, its owner, the permissions, the timestamps, the size, how many names point to it, and crucially, the addresses of the data blocks where the actual content lives. But notice what's missing from that list: the file's name and the file's contents. Neither is in the inode. The inode is the file itself. The name is just a label hanging off it. Let's open that record up. In roughly 128 or 256 bytes, four things live side by side: an identity, the inode number and the object's type; ownership and mode, which is where access control actually resides, not in the directory entry; the times and size, including that link count that quietly decides when a file gets deleted; and finally, the block pointers, addresses into the data. That last field has to fit in a fixed space, and that's where the design gets genuinely clever. Here's the trick. The inode holds 12 direct pointers, enough to address a small file, about 48 kilobytes, in a single hop. When files grow larger, one slot is repurposed to point at a whole block of pointers, then another at pointers to pointers, and a third at yet one more level. 4 tiers reaching from kilobytes into terabytes, all from the same fixed record. Small files stay fast, huge files pay a few extra lookups. That asymmetry is elegant, and eventually it's exactly why extent-based designs took over. Which brings us to a failure mode that looks impossible on paper. Writes start bouncing with disk-full errors, but df cheerfully reports the volume is only 40% used. Run df with -i and you see it. Inode usage sitting at 100%. You didn't run out of bytes, you ran out of records. Some mail queue or session cache or forgotten build directory spawned millions of tiny files, each claiming one entire inode. And because that pool was sized when the volume was formatted, you can't grow it. You can only delete or reformat. Once you see the inode as the real file, 3 familiar operations suddenly separate into very different animals. A hard link is just a second name pointing at the same inode. There is no original, no copy, and the link count on that inode simply ticks up by 1. A symbolic link is something else entirely, a tiny file whose contents are literally a path string, which is why it can cross file systems, but also why it breaks the moment the target moves. And a copy, that's a brand new inode with its own data blocks, related by history but independent from the instant it's made. And that same shift in perspective is what opens the door to everything coming next in this series. Hard links and symbolic links we've just touched on, but each really deserves its own episode. Permissions, journaling, extents, and the virtual file system. Every one of these sits on top of the inode we opened up today. Next time, we'll follow the thread into permissions and see how identity and access are two very different questions. So let's leave you with 3 things worth carrying forward. The inode holds everything about a file except its name and its contents, those live elsewhere. Indirection lets a small fixed record reach an enormous file, trading a few extra lookups for that reach. And because inodes themselves are finite, a disk can run out of files while still full of empty space. The name is just a label, the inode is the identity. Thanks for watching. I'll see you in the next one.